Thank you all for coming in, for joining. Let me introduce a speaker and we'll get right to it. So Dr. Abdulrahman is a postdoc researcher in computer science at Harvard University, where he's working with Dr. David Brooks and Dr. Guion Wei. His research interests are broadly in the areas of computer architecture, machine learning, reliability, and approximate computing. His work focuses on addressing the role hardware errors play on an application's error tolerance by designing tools and techniques to help understand how hardware errors propagate and affect software. Abdulrahman has completed his PhD at University of Illinois at Urbana-Champaign under the guidance of Dr. Sarita Adway in the RSIM research group. During his graduate studies, he was very fortunate to be the recipient of MEVIS Future Faculty Fellowship, to be invited to the 7th Heidelberg Laureate Forum, and to receive multiple awards for teaching and mentoring undergraduate students. Prior to joining University of Illinois at Urbana-Champaign, Abdulrahman had completed his Bachelor's of Science in Engineering from Princeton University, where he was also the recipient of the John Ogden Bigelow Jr. Prize in Electrical Engineering. So with that introduction, I'll let the speaker take it away.
Sure. Thank you so much for the kind introduction and for having me here. It's a pleasure to be here virtually with everyone. So I guess I'll go ahead and get started then. So today my talk is about towards scalable and specialized application error analysis. And the main motivation behind this work is that hardware errors are prevalent. Given that the past few decades, we've been writing Moore's law and Dennard scaling for increased processor performance, and transistors got smaller and smaller, and we were able to benefit from that. However, as technology scales, it also is more susceptible to transient errors or soft errors from things such as high energy particle strikes, wear out, or from voltage groups. At the same time, the number of devices is growing very large, very quickly. And so the scale of these devices increase the likelihood that an individual component can fail. So there's a lot of real world consequences that can come across, can happen because of this. So a couple of years ago, there was a Toyota lawsuit where basically they showed that as little as a single bit flip could make a car run out of control. In Belgium, there was an election, and they said that a cosmic chain of events caused a single bit to flip and call the outcome into question. The motivation for this work in the Moore's law and Dennard scaling gives us smaller transistors. These smaller transistors are more susceptible to transient errors, and the number of these devices means that these transient errors are more likely to appear and cause individual component failures. So these hardware errors can be very bad. I gave two examples here, which is the Toyota case and the Belgium elections. And I was going on to talk about how earlier this year, Meta sent out a proposal for silent data corruptions at scale, asking for calls, because what they thought was a 1 in a million occurrence for bit flips, they were able to show that is only a 1 in 1,000 occurrence. And it affects their fleet of hardware. And of course, they want to mitigate these type of problems. By the way, feel free to interrupt at any point in time. I have a couple of stop points in the talk if you want to ask questions, but feel free to interrupt at any time. So, given that this is a huge problem, it actually, people have been addressing it and dealing with it for quite a long time as well. And so reliability in practice, there are two main components. There's storage and memory protection. And so typically this involves either parity or error correcting codes. And this may not be enough to fully protect your hardware from compute errors. So protecting computation usually involves dual modular redundancy of some sort. So either re-executing a application either in time or in space on two different hardware units and comparing the results. But the problem is this usually incurs a 2x overhead in either area, power, latency, and other metrics that are typically pretty important in computer architecture. But despite the overhead and the cost, it's still pretty much the state of the art to be doing that. So Tesla's recent full self-driving chip, where they basically have a neural network running on their own custom processor, they basically have two processors which are entirely redundant for this specific problem to make sure that their fleet of cars don't run into these type of issues. And so this is still considered the state of the art, even in 2019, in the 21st century, despite it seeming to be quite expensive. And so one of the questions that we ask is that, isn't full redundancy overkill? Because not all errors are bad. And I give two examples here. One of them is for deep neural networks, where we know that there's some sort of built-in error tolerance in these models. And they do pretty well, even despite the not even being full accuracy from an algorithmic perspective and classification and stuff. And so this shows that maybe full redundancy isn't the way to go for things like neural networks. Another example is the whole field of approximate computing, where people have shown that you could trade off certain computations and some accuracy and still get pretty significant performance benefits. So giving up a little bit of quality usually gives you a lot of performance benefits. And this shows that full redundancy isn't always necessary, because maybe you can give away some of that redundancy and still be okay. But that's not always the case. Some scenarios, for example, in self-driving cars, you might not even want to be partially approximate, and you might actually want a lot of redundancy to make sure you don't have fatal accidents. So for example, classifying a truck as a car, instead of applying the brakes, you speed up, and that would of course be horrific. So today I'm going to be talking about our solution to this problem, or a possible solution to the problem, which is application-driven selective low-cost protection. And there's three parts here. The application-driven part is basically trying to tune our resiliency for the application on hand. So understanding the software in order to mitigate hardware errors. And also to perform selective duplication, selective protection, in order to still get very high error coverage, but hopefully with very low cost overhead. And the questions we have to ask in order to achieve this selective low cost protection is what has to be protected? So what granularity do we have to basically target our protection? Where do we perform our protection? And this requires some analysis and understanding of the application, hardware, and software. And third, how do we do the protection in a low cost manner? And to kind of give a summary early on kind of what you'll see in a couple of minutes, is that we introduced three techniques for optimizing selective protection for convolutional neural networks. And we focus here on CNNs because they are predominantly used in many safety critical areas, such as self-driving cars, and that's important to make sure that they're reliable. And so the first technique that I'll be talking about is called feature map level resilience, which is the idea is to basically identify which feature maps within a neural network are the most vulnerable and to protect them even before deploying the CNN. And to do that, we introduce a new metric called delta loss, which helps us identify which feature maps are more vulnerable 3 times faster than the state of the practice and the state of the art. The second technique I'll be talking about is inference level resilience. Here, rather than trying to find which components in the neural network are vulnerable, to basically see if there's some temporal vulnerability. So are some images perhaps more vulnerable than others? And if you see them, you're more likely to make a misclassification when an error occurs. And so we basically try to capture the relationship between inference and the output confidences, and when an error is likely to affect that. And third, we show that the combination is better than the sum of its parts. So combining FLR and ILR, we basically can have this optimization problem to basically figure out how much FLR is needed, how much ILR is needed together, and to get very high coverage with less than 2x overhead. And when we implement this, we actually show that in practice, you could actually get away with less than 2% average overhead on a edge-like platform, which would be typical in a self-driving car type of environment. So with that, I'll basically dive right into the 3 components. So I talked about the motivation and the overview, and then I'll give more details on FLR, ILR, FILR, and then conclude with some future work that is interesting here. Okay, so the first technique I discussed briefly was feature map level resilience. And the idea here is that we basically want to take a software-directed approach, an application-directed approach for hardening convolutional neural networks during inference. So the general framework that we have is to understand what is the granularity you want to perform protection at. In a neural network, you could either do the full network, the entire network, you could protect certain layers, you could protect certain feature maps within a layer, or you could protect at the neuron level. So I'll talk a little about that. And then once you decide on the granularity, how do you rank or how do you decide which feature maps or which neurons or which layers are the most vulnerable and need to be protected? So we have to efficiently estimate the neural network component vulnerability. And third, once we decide on which feature maps need to be protected, how do we perform the protection in a low-cost manner? And I'll mention that all of this is entirely done in software with the intention that this can basically run on any hardware platform backend. So whether you end up running your neural network on a GPU, on a CPU, or a future accelerator, this application-directed approach, the software-directed approach, should still work regardless. And that's kind of the key behind the portability of this technique. So let's talk a little about the target granularity. So I mentioned this computational hierarchy in a CNN. And so we assume that storage is protected or can be protected with something as parity or ECC. And what's really important, and in the context of neural networks, is the majority of what needs to be protected are the computational errors. And neural networks are typically very compute intensive. And so neurons are basically the output of a multiply and accumulate operation. You have an input feature map, you convolve it with a filter, and you get a single neuron. And you do this over and over again. And a group of neurons is basically your output feature map. A group of output feature maps performs your layer. So this is the general neural network design that is commonly used in convolutional neural networks. And we basically have to decide which is the right computational granularity to target. And so we target feature maps for two main reasons. The first is their robustness to translational effect. So neurons, as opposed to feature maps, their values can actually change based on the rotation of an object. And so if you have more white space in an area, the neuron might be different. Whereas feature maps, even if you do some things like a translation, the feature map should still capture this effect in an image and still classify it correctly. And so feature maps capture features, basically, which is the algorithmic type of effect that we want to protect. And if we compare between layers and feature maps provide us with more granular options to basically choose which places to protect. And so if you look at the table on the right here, common neural networks and how many layers they have and how many feature maps they have. So a layer, if, for example, for AlexNet, you only have 5 layers. So if you protect a full layer, you might be protecting a significant number of feature maps, some of which won't need protection. So by basically decomposing it into feature maps and focusing on feature maps, then you basically have a granularity that you can target and hopefully get this selective protection that we are targeting. So given that feature, so we can do the similar technique for neurons, feature maps, or layers, but we focus on feature maps because of the reasons described here. So here's the crux, basically, of the FLR technique, which is how do we perform the vulnerability estimation? So we accepted that feature maps are the way to go, but how do we basically decide which feature maps are more vulnerable than others? So let's go through this equation together. So basically, the vulnerability of a feature map is composed of 2 parts. Well, the first is the origination vulnerability in the feature map, and the second is the propagation vulnerability. The origination vulnerability is basically a characteristic of the hardware. So the likelihood an error originates from the feature map within a network. And so the particle strike hits this specific feature map in your hardware during the computation. So what is the likelihood that that happens? And the propagation probability is, given that an error occurred in this feature map, what is the probability that it propagates all the way to an output and corrupts your final output? And so what we basically want to do is figure out for each feature map, what is the relative vulnerability compared to the entire neural network. So for all the feature maps, which ones are more vulnerable than others, and then we could basically do a knapsack type of problem to decide which ones should be protected, which ones we can we don't have to protect, and correspondingly how much overhead we basically incur by protecting these feature maps, because that feature map, some can be larger than others, and so on. So this is the general idea here for deciding on the ranking for feature maps. So I'm not going to talk much about the origination vulnerability because, again, it's a function of the hardware. And so we can basically assume it's the number of multiply and accumulate units within a feature map. But I'll talk more about the propagation probability, which is a kind of an important aspect here, which it's harder to model and actually has to be tested. Sorry, Ahmed, do you have a question?
No.
Oh, sure. Okay. So talking about the propagation probability. So there's different ways to basically measure this probability. The first is the ideal but impossible approach, which is the exhaustive approach. So we basically want to model or basically implement a single bit flip in every single possible bit of a feature map for all possible inputs coming into this neural network. And of course, this is infeasible, it's intractably large, and it's not possible. So other ways that we could kind of still gauge how vulnerable a feature map are, we could either do statistical error injections, which can be pretty accurate with statistical significance measurements, but it can still be slow because you still need a lot of error injections in order to get your statistical significance. And the third approach is a heuristic approach, which can be very fast, but might not be as accurate because it's a heuristic and it's basically a guess of some sort about the ranking of the feature maps. So I do have some work on the heuristic approach, but we were able to verify that it's fast, but not as accurate. But today I'll talk mostly about the statistical error injection approach and how we could benefit from the accuracy perspective while mitigating the speed problem, which is that it's still pretty slow. So we developed this tool called PyTorchFI to perform our error injection. So it's a runtime perturbation tool for DNN built on top of the PyTorch framework. And it's open sourced, and I encourage you to download it and let me know if you have any questions or comments, and a shameless plug here. And basically, we use this to do all our error injection experiments. And then what we do here is that we take a neural network, we go into each feature map and we flip a bit and we let it propagate to the end and we see what happens to the final classification. So if your input image was a dog, for example, or a car, and you flip a bit, does it turn out to be something other than a dog or a car? And conceptually, you basically figure out how many number of yeses, how many mismatches occurred versus how many total number of injections you perform, and that gives you a probability, the propagation probability for that feature map. And you could use this to basically rank different feature maps, which ones are producing more errors on the output versus which are producing less, and use that going forward. So this is great, this is standard, but it's extremely slow. And the reason it's slow is because, like I mentioned, deep neural networks are quite robust in general. And so even if you get a single bit flip, it might not cause you to produce a mismatch. And you will have to take a lot of error injections to actually increase this probability to something more significant than 0 or 1, which a lot of things might appear as that way. So one of the key insights in this work is to change the binary view of an error propagation, instead of just mismatch or not mismatch, into a continuous view. And this gives us a lot more information per error injection experiment that we want to perform. So we introduce this concept of delta loss or cross entropy loss, the difference of cross entropy loss, as a continuous metric for error propagation. So cross entropy loss is actually a commonly used metric in training, and we adapt it here for the resiliency analysis of CNN. And so I'll show here what it is via example. So we have here an input of a car, for example, and a classification, say 83% car, which is the correct classification. And this is what the neural network should output, assuming no errors. What we could do here is we could compute this cross entropy loss, and it's a simple formula. And a cross entropy loss of 0 would imply perfect confidence and accuracy in the prediction. So it would say 100% accuracy of a car would give a loss of 0, and anything less will give something larger than 0. So we could capture this with a number. Here's 0.18, for example. If we do an error injection and we see that a mismatch happened, a misclassification happened, in the previous formulation, we basically increment that counter of yes to +1. And we basically want to count how many times this happened as a function of the error injections. So what we're proposing here is that rather than just counting mismatches, let's capture this loss, this cross-isotropy loss, and find the difference between the originally correct and the incorrect delta loss, or the incorrect loss value. So this is all good and great, but so far there's no real difference between mismatch and loss. The big difference comes when an error injection occurs and it changes the output, the softmax, the final classification of the percentages for classification, but it doesn't actually cause a cost to change, a misclassification to happen. So in the previous way of computing or calculating mismatches, this would not be considered a mismatch, and you would basically not have anything to use from this experiment. Whereas the delta loss, the difference in loss, it basically increased. So from 0.18, it went to 0.54. And you could basically capture this magnitude in the difference, saying there's a sensitivity, something happened here. And what you could do is basically average across a bunch of these error injection experiments to see how sensitive a feature map is to an error injection. And this is exactly what we do. So the metric we introduce is this average delta cross-entropy loss. And so we capture the golden inference loss and find the magnitude difference from all injections and average across all the injections we perform. So once we have this, we can basically get a propagation probability for each feature map, and we can get this relative probability for a feature map and use that to rank and sort feature maps which are more vulnerable than others. And we could also do this very, very quickly, as I'll show in the next slide. So one of the things we have to double check though is how accurate this metric is compared to mismatch, which is the standard state of the art, what everyone uses and is the golden comparison that we want to compare to. So we performed this experiment where we introduced a statistical oracle, so a large number of error injections, here it's 12,000, which gives us pretty high confidence and a small confidence interval. And we perform a sweep from 64 injections per feature map to this 12,000 and measure both mismatch and delta loss. We then compare the ordering of the feature maps between the oracle, which is mismatch at 12,000, with all the different orderings we produce in the sweep. And we compute the Manhattan distance between the cumulative distribution functions of these two rankings. So we can basically get a single data point for each comparison between two rankings. And what we could do then is that we could basically see at each number during the sweep for a number of injections per feature map, how far are we from this golden ranking of our statistical oracle. And so on the x-axis here, we basically show the injections per feature map. And on the y-axis, we show the Manhattan distance. And another way to look at the x-axis of 0.01, 0.02 is also a percentage. And so 0.01 basically implies 99% similarity to the oracle. And so most of the time, it's actually pretty close. So it's always within 10%. But the interesting thing, and we actually want to target very high similarity, is that at largish numbers, so at this 12,000 statistical oracle, both of these seem to asymptotically, empirically converge, which is important to basically give us confidence in this delta loss metric. At the same time, if we basically look at when the delta loss metric reaches this 0.01 versus when mismatches reaches this 0.01 for 99% of the oracle, on average for a specific network, delta loss does it 3x faster, and sometimes as high as 10x faster for certain networks like ResNet and so on. And this is basically a validation to give us more confidence in this metric of delta loss.
Sorry, Abdulrahman, question.
Yeah, sure.
So the idea of fastness or speed here is not in terms of time, it's in terms of number of error injections, right?
Yes, which correlates directly with the time because all these experiments are done, well, yeah, so it's compute resources. So yes, they could be done in parallel. But the idea, for example, is that instead of doing 12,000 injections per feature map, you only need 2,000 samples. And that's good enough, for example, to get a quick feel of the ordering and still be pretty accurate, correct? Yeah.
Thanks.
And this is an offline cost. So hopefully this is only done once. And then once you have the feature map ordering, then you could protect it, which is what I have on the next slide. Yeah. Cool. So once you have this ordering, how do you do the protection in a low-cost way? There's many different ways to do it. We choose a simple way, which is filter duplication, because filters and feature maps are one-to-one. And so in software, we could basically duplicate the filters that correspond to the vulnerable feature maps. And then when the neural network is propagating, it just recomputes the ones that we have, or computes them because they're duplicated already, compares them, and then just drops the computation if everything turns out good. If anything turns out incorrect, it flags the system that there was an error that happened. And this could also be done off the critical path because you could proceed to future layers as the previous layers are doing the computation as well. So that's also a benefit here. Excuse me. So once we basically can do this type of analysis, we can have this tunable space where a user could basically say, okay, I'm going to target, say, 50% coverage or 90% coverage. How many additional MAC operations, how much computational overhead do I have to spend in order to attain the overhead, in order to attain the error coverage that I desire? And we could basically produce these plots, and we have two main takeaways. One of them, the first one, is that the overhead is always sublinear to the coverage. And this kind of goes back to the fact that this is certainly better than 2x overhead of dual modular redundancy. So selective protection here definitely provides something useful. And the second thing is that for some networks, we could get a very strong or very big reduction. For example, SqueezeNet, a 10x reduction. A 10x reduction, meaning 90% coverage with just 30% additional computation. And this is a pretty high benefit compared to this previous state of the art, which is just duplicate the entire computation and make sure everything is safe. So this is a pretty powerful technique, but it works for some networks, not for all networks here. And that's basically the main takeaways for FLR, for feature map level resilience, where it's a software directed solution for targeting feature maps based on the key idea that not all feature maps are equal. Some are more vulnerable than others. But the one drawback, which I alluded to on the previous slide, is that if you want to target really high coverage points, it still might incur relatively high overhead. So you have this sudden sharp rise towards the end. So you can still benefit from it, but you might want to do benefit from something. If you could get something better, that would be good. And I'll talk more about what can be better next. Okay, let me move on. I think there's a lot of interesting stuff comes up later too. But again, feel free to interrupt at any point. So inference level resilience. So I spoke a bit about FLR, where the granularity is targeting neurons or feature maps or layers, and we chose feature maps. And the key question is, how do we decide which feature maps need to be protected? And the protection technique would be through feature map duplication. So the filter duplication for the feature maps. So this is another technique called inference level resilience, where the granularity is for a full-on inference. So it's actually a network level. And the protection technique is to rerun inferences which are deemed vulnerable. And the key questions here is how to determine something is vulnerable or an error may have just occurred post the fact that it occurred. So for this technique, we leverage, again, two key insights. One, that despite their importance, the errors are infrequent. And so one of the drawbacks of FLR is that you're basically building in or bulking up your neural network, doing duplication all the time. And so if there's a way to avoid doing that duplication unless it's necessary, that would be advantageous. And the second question is more of a hypothesis at this point in the talk, is the effect of an error related to the output confidence? So when you see that you are 90% that the confidence of the car is the car, do you expect an error to have occurred or not? And I'll show here that there is a correlation between an error in the output confidence. And the way to do it is basically to selectively perform inferences to rerun them based on some analysis here. So again, as by form of example, ILR is designed like this. So we perform all inferences normally. So you have an image of a car, you run it through a neural network, you classify a car. And we attach this little piece of code at the end of a neural network that says, if something happens, re-execute the neural network. Otherwise, don't do anything. And the conditional statement here is, for now, if the top one confidence is less than a specific threshold, then rerun. Otherwise, let everything go forward. So for example, if we set the threshold as 90% confidence, if we ever get a classification of car with less than 90% confidence, we have to rerun it just to make sure and compare that this is what happened. So we perform 40 million error injection experiments here to test this idea, and we measure coverage and overhead. So the coverage is basically how many output errors occurred that we're protecting against by rerunning. And the overhead here is basically the rerun overhead, so the duplicate inference, and how many computations as a result of the rerun. And we could basically sweep the coverage threshold. So we start at 0% to 100% and see for each threshold, how much coverage are we protecting against and what is the overhead, the corresponding overhead. So we basically can produce these types of plots per network. So here, this is an example for ResNet 50. And each dot here is a different threshold. And for each threshold, on the x-axis, it shows what coverage I'll be getting. And on the y-axis, what is the cost I'm paying for how many things are going to be rerun. So for example, if we decide the threshold is 51%, meaning any inference where the top one confidence is less than 51%, rerun it, we'll catch 90% of the errors, and we'll be incurring only 18% overhead roughly, which is a pretty good trade-off here. But can we do better? Again, if we want to take into account the actual confidence, the domain-specific insights here, top one confidence, for example, in these two neural networks, would say, if we set the threshold as 51, would say don't rerun either of these neural networks. So the top one, 83% confident, don't rerun it. Second one, 58%, don't rerun it. But what we found is that even a better metric to decide if something needs to be rerun or not, so it's a better vulnerability assessment, is the difference between the top two values rather than just the top one confidence. And so in the top case, if we look at it, the difference between the top one and the second one is 72%, whereas in the bottom example, it's only 22%. And the intuition here is that for an error to actually corrupt your final output, it has to cause your top one class to change. And so if the catalyst, if that difference is small, you're more likely to get errors, whereas if there's a big gap, an error might still affect your final classification accuracy or top one confidence, but it might not be enough to make you flip to another class. And we validate this, and we actually find a direct inverse correlation between the top two diff and the output misclassification. So for all these networks here, we basically take the inference for the images without performing any error injection. We perform various error injections, and we find that for images that have a small top two diff, they are more likely to produce misclassifications compared to images which had a very large top two diff, meaning the network was pretty confident in their classification. And what's even more interesting, if you could see even here for the scale on ResNet 50, is that it's actually way higher than the typical error rate that you'd be expecting. So on average here, so we said like in Meta, they saw this 1 in 1,000 effect. And we typically saw less than 1% of errors across all our experiments. But if we only focus on small top two diff, we see this number rise or jump suddenly to 20%. So for 18% here for ResNet 50, which basically tells us that if the network itself isn't confident in the output and this difference is small between the first and the second, an error in your hardware might actually, or with very high probability, will cause your output to flip. And this is very core to how these errors are actually manifesting themselves in these things. So we could perform a similar experiment where instead of using this conditional as top one confidence, we could change it to top two diff. And what we find is that this top two diff has a slower knee for threshold selection, meaning that we can actually get higher coverage at much lower overhead because we're actually getting much, much closer to the real reason, the core reason why errors are happening, as opposed to a secondary or perhaps an auxiliary metric like top one conf. So with ILR, it actually does pretty well. And so we here show again the difference between top one confidence and top two diff. So if we target 90% coverage, so 90% output corruption coverage, and we want to mitigate them, on average with top one conf, we'll be paying 31% overhead, and with top two diff, we'll be paying 17% overhead, and as low as 9% for networks such as ResNet 50, which is a pretty good trade-off. So you're getting 90% coverage with almost 9% overhead, much better than the dual modular redundancy. So this is, again, great, but there's still this sharp rise in the last few coverage points. So bridging that gap between 90% coverage and 100% coverage is still pretty expensive, shown by this sudden rise here at the end. For the third technique, which is really just a combination of the first two and converting this into an optimization problem, is how much FLR do you need versus how much ILR do you need? And when you combine them together, how well does it perform? So the high-level algorithm for FILR is that we first run ILR and we identify different top two diff thresholds. And then for each threshold, we'll basically run FLR with the objective of protecting the feature maps, which ILR was not able to protect against, the errors that ILR was not able to catch. So we target the errors that ILR was not able to catch. And then we basically just find the optimal coverage overhead point, which is how many feature maps to cover and what top two diff needs to be implemented, what top two diff threshold needs to be used. So intuitively, the difference between these two techniques is that FLR kind of makes your DNN larger in that you're embedding static protection into your network. So you're duplicating filters to rerun the computation for the feature maps. Whereas with ILR, you're doing your protection after the neural network, and it's basically a temporal protection mechanism. And FILR basically says, let's put them both there and optimize how much protection you have to do statically and how much do you have to do dynamically to get the best of both worlds. So here are the results for FILR. So we're targeting here 100% coverage based on our experiments. And on the x-axis here, we have the different top two diff thresholds for ILR, where on the leftmost, so 0 top two diff threshold implies you're basically just using FLR, you're not doing anything with ILR. And on the right-hand side for a top two diff threshold of 1 means you're rerunning every single inference because your threshold is the maximum value. And in between, you basically have all these various points, which we basically show that there exists multiple, in some cases, sub 100% coverage points that also produce, sub 100% overhead points, which give us this 100% coverage that we're targeting. And so, for example, for ResNet 50, you would only need to set your top two diff threshold as 0.2, and you protect the feature maps that correspond to the remaining protection, and you're only going to pay an overhead cost of 20% combined between FLR and ILR. And we validate this result. So the previous slide was our analysis saying, okay, so let's target 100% confidence. What do we actually, coverage, what do we actually get? And so we use a different test set. We do random error injections. We use the values that we computed previously during the analysis phase. And we still get very, very high coverage, 99.78% on average. And across the board, it's less than 50% overhead, with some networks such as ResNet getting as low as 20%. And so this is really good. One might consider these values still relatively large. So reminder that overhead here is the number of computations that are increased. But hardware is still relatively optimized. And so when we run the same experiment with the implementation of FILR on a NVIDIA Jetson, which is an edge-like device, we find that the actual overhead we're seeing on a CPU is on average 7.5%, and on a GPU is less than 2%. And so basically, there's a lot of these computations that are actually still hidden. And so even though you're doing 20% more computations, some of it is still optimized away with the hardware that you're using. So now you're getting nearly 100% accuracy with less than 2% overhead using this selective protection techniques. So it's a high-level summary of the three techniques. Feature map level resilience is targeting the statically protecting feature maps before deployment. Inference level resilience is a more of a dynamic approach. And it produces low-cost, high-coverage techniques. And FILR is the best of both worlds, especially when we go ahead and implement it in hardware. So I'll pause again here before moving on to some future work. If anyone has any additional questions about anything that passed or FILR in specific. If not, I could move on to some interesting future work that some of it I'm currently doing and some of it is more broad and long-term. So one of the key things that we found during this implementation, by looking at things from a software level, but considering hardware errors, is that there's a lot of similarity between different types of perturbations in general in this domain of neural networks. And so while most of my work has focused on transient hardware errors, things like adversarial errors or just errors in confidence, for example, in neural networks, there's a similarity between them that exists, but it's not totally been honed in on yet. So using the PyTorchFI tool, we actually started playing around with some of these other nearby domains. So instead of modeling errors as a single bit flip in hardware, to look at it more as a general perturbation, and these perturbations can be modeled in many different ways. And so I focused mostly on classification here, but we also looked at things like object detection, model training, security, interpretability. And we're able to show that when you consider errors in general, you could do some very interesting things. For example, if you could train models using specific errors introduced in the model in a very specific way to improve the training accuracy significantly. And same thing with security. One way I like to think about it is that resilience is kind of a subcategory of security where your adversary here is just environmental effects, whereas for security, you have an actual adversary that might be more clever. And so instead of a single bit flip, they might be doing something much more nefarious. And so it just kind of is a generalization here where we could still use the same sort of techniques, still use this faster methodology for using delta loss instead of mismatches, and still go about some of these very different and interesting problems in similar domains. So one thing is going from hardware errors to general perturbations. Another interesting future work, and this will be upcoming at DSN in later June, is trying to understand the impact of numerical data formats in neural network accelerators. So a lot of times whenever people talk about single bit flips, they implicitly assume floating point, 32-bit floating point. But there's a lot of new numerical data formats that are coming out. So for example, block floating point, there's adaptive float, quantization with int8. And all of these different number formats, it means a single bit flip means something different in each of these different formats. And so we actually just released a tool called GoldenEye. And the objective of this tool is to kind of open up the hardware to the developer and software to kind of play around with different hardware format, numerical data formats, and see what effects the number format has on the resilience of the accelerator. And so just to note that most of the results I've shown here were tested on both floating point 32 and int8 in the whole talk. But with GoldenEye, you basically can look into things like block float, which is a pretty nice way of improving efficiency in neural networks and see the resilience of that, and adaptive float, which is also, again, aimed at efficiency, but we could evaluate for resilience. And last but not least, but this is more of a really out there, is there a unifying theory for error analysis? And so I mentioned in bullet point 1 here that errors can appear in many different contexts within DNNs themselves, but they also come across in many different topics in computer science in general. So are there some general principles that we can adopt? And so most of my work here is on silent data corruptions. We could extend it to security vulnerabilities, but even things like,
Sorry.
Go ahead, yeah.
There's a question, I think.
Oh, sorry, I missed it. Go ahead.
Tanu has a question. Might want to unmute yourself.
Sorry. Yeah. So just stopping you in between over here, I sort of, have a question that how do you distinguish between that, there has been the change in the system has been because of a hardware failure. Like here, the cause is a hardware failure because as I understand, you are manually injecting that cause or manually assuming that is the cause. Let's say someone runs the DNN again and there is a different accuracy result. How does even one come to know whether this is coming because of a hardware failure, or is it just because of non-determinism, or just because in the software there has been some change in the order of the operations? So
it's a really good question. Yeah.
I'm just trying to, I must say I'm not very familiar with how DNNs operate. I'm new to machine learning, and so I'm getting a sense of it, but I've been working on this area of error analysis, and I'm trying to figure out how do you determine that?
That's an excellent question. So in the context of neural networks, we do expect it to be deterministic, because otherwise you're right, things are, it's hard to pinpoint what the source was. And so neural networks specifically, we expect them, if you pass in the same image multiple times, you'll get the same output multiple times with the same confidence levels, presumably. And so there isn't any non-determinism. But your question is excellent in terms of there's many sources of errors. Identifying that an error occurred and kind of tracing it back to figure out the root cause, that's a very valid question that kind of goes more towards this unifying theory that I don't have an answer for, unfortunately.
Okay.
But yeah, in the context of neural networks, thankfully, I guess it's still deterministic. But I do love the direction that you're suggesting here. Yeah.
Okay, great. So then you and I are on the same page.
That's good. Perfect.
Okay.
Yeah.
Okay. Cool.
Yeah, I've had some thoughts, but I never thought about it from a non-deterministic perspective. Kind of still thinking about it in terms of these things like a bug in software is still an error. Maybe it's a human error, but it's an error. And so when do we protect against that and versus hardware error versus security flaw? And that's kind of the main idea here, is that these are all very similar. And there's also rounding error. So in a neural network, you think of accumulation error and things like that, and the effects it has on your final accuracy. Right. And that's one of the reasons why actually my work is moving more towards application level resilience. Kind of that's a motivation here, is that when you understand the domain more, you could do some of these nice, interesting tricks like ILR, FLR, where you can't do on general purpose compute because you don't know the domain. You might still have to protect everything blindly because that's what you want to go with. Yeah, and actually relating to your question, I was kind of thinking of very different ways of thinking about errors, and just have a list of things here. Again, no answer, but I think of errors as security. There's quality of service guarantees, good enough. What is considered good? Even software testing. The most interesting thing I think I found about this is that in the software testing world, people ship code that's buggy all the time. Yet it's still being used left and right, and in so many safety critical environments and domains, like just banking and stuff like that too. Yet there's a methodology and there's a way to kind of go about it to make sure it's good enough to release to the public, and you patch it along the way. I don't think there's something like this yet fully exists for neural networks, yet they're already being deployed. But I know there's definitely some things we could benefit from the software testing world that I have some work on, but still it's barely scratching the surface. And there's other things like the infrastructure, the power grid, recommendation systems, and how do you know something is right? So the word error in my mind it kind of comes off as a negative word, but in my mind, I think there's so much opportunity in trying to figure out what comes, basically the 1- error side of things, the approximate computing side of things. So yeah, I don't have a specific answer, but I think that's a really interesting direction that I'm also interested in working on.
Right. So I would say that, in one way, I would look at this as sensitivity analysis as well, instead of error, which, as you're saying, is more a negative connotation to it. But it's essentially how sensitive is your program with respect to, as you're, flipping the bits, or with respect to in a particular layer being vulnerable to the changes. Because I mean, if you flip a bit, essentially you're saying that that's how the image, there might be a low quality image in which the bit over here, which was 1 and 1, is now 0, right? And some bits have been flipped. And if there's a low quality image or maybe higher quality image, then how does the performance or the accuracy of the neural network change, which could itself be like a data set change? It is not necessarily an error propagation as much as, well, a different data set came, and how sensitive is my model to the whole thing. So yeah, I think this is fantastic.
Yeah, I like that framing of sensitivity analysis is the big picture here, and you could call sensitivity analysis errors in certain subcontext. But yeah, that's absolutely
right.
Yeah.
I mean, software testing sensitivity analysis is a very common term that's used. Yeah, and sort of, you have some interesting sort of things over here as well, in the sense that so I sort of work in reproducibility, which is kind of what this is also about. Like, if there is an error that comes in, and what is the cause for the error, and we have this notion of a dual execution, right? That well, you when you run a program, you'll have to run it twice to get an idea about, well, you run it first, so you'll have some that you have a correct picture in some senses, and then you have an erroneous picture, and you have to run them twice so that you can compare the original with the erroneous. But the way I'm seeing in your work, you're sort of doing sort of maybe error propagation or error quantification, in which case, as I'm understanding, you don't have to run it twice, or you're even avoiding the redundancy of doing a computation multiple times.
Yeah. And I think this is mainly here because kind of we're assuming it's correct unless one of our anomaly detectors kind of flagged it as potentially incorrect. Right. Yeah, exactly.
Okay. Thanks for confirming. Excellent work.
Great. Thank you so much, and thanks for this great discussion. Yeah, that's actually my last slide. I am very much interested in the last bullet point, which is error analysis across different domains, and sensitivity analysis. I like using this word. So yeah, it's been a pleasure here. I don't know if there's any more questions. I'm available